Yeah.
懐かしいです。
You remember?
はい。また行きたいですけど。
ああ。
先生。先生、元気ですか？私、旧大アルムナイ。
Yeah. Okay. Ore.
Kak Idris, apa kabar?
Baik. Hebat. Corona.
Dear panelists and also attendees, right now we are still waiting for Professor Akrajas Ali Umar, who has not been signed into this meeting yet. We have emailed him one more time, and I think it will be wise if we wait for him for 5 minutes more. Is it okay? Before we start the meeting. Thank you very much for your understanding. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Honorable keynote speakers, excellencies, ladies and gentlemen. Good morning. Alhamdulillah. Today we meet the second day of our seminar, International Seminar on Science and Technology 2020, and we are still able here to attend. Thank you very much also for the keynote speakers and also for the panelists who still managed to come today, Professor Dahlan Tahir. And also thank you very much for all the attendees from all over the place. Also, we can see here attendees from Japan also attend this second day, and also from Malaysia and also in Indonesia. Thank you very much. So we are going to start our second day of seminar with the first presentation by Professor Koichi Somori from Department of Applied Chemistry, Miyazaki University, and also maybe will be followed by Dr. Idris Mandang from Hydro Atmosphere Environment Research Group, Department of Physics, Mullah Warman University. And while waiting for Akrajas Ali Umar to join our meeting. Okay, at first, let me introduce Professor Koichiro Shiomori. Pak Elisa. What? Man.
Oh, yeah.
Okay, Professor, still waiting for, I'm sorry. Okay, Professor Koichiro Somori is a professor from Faculty of Engineering. Research field is nano and material reaction and separation from Miyazaki University, Department of Applied Chemistry. Okay, he also the alumni from University of Miyazaki, majoring in industrial chemistry, and also he finished his graduate school from also University of Miyazaki, Japan. His field of expertise is about the chemical engineering process, transfer operation, unit operation, biofunction, and also bioprocess. Okay, and also has a lot of papers related to his expertise, and also has many cooperation with other university like from Mongolia, and also from Indonesia, and from India, and also from Bangladesh, if I'm not mistaken. Okay.
Yeah, but I'm sorry. So my PC was freezing.
Okay. Pak Elisa,
So,
would you please stop screen share now?
okay, so
Okay.
can you?
Shiomori Sensei, you can share your screen.
Oh. So not. So not no. So my PC not working. So no response.
Oh, sorry, Sensei. Maybe you can leave the meeting first and also re-enter again the meeting. Maybe it will solve the problems.
Yeah.
Okay, we will wait for you. So please first leave the meeting and join the meeting again.
Oh.
Okay. Okay, it's good.
Okay, so you can see my screen. Okay. Okay. Okay.
Okay, we
Oh,
can see very clear. We can see your
okay.
presentation very
Thank
clear now.
you. So I'm going to start my presentation. So today I will show recent development of microcapsule and polymer particles for separation medium. So at first, I would like to introduce Miyazaki and also our university. So this is a Japan map. So I'm here and Kyushu Island, east coast of Kyushu Island. So Miyazaki Prefecture is around here. So our University Miyazaki, have 5 faculty. So agriculture, education, regional innovation, engineering, and medical school. We have about 5,000 students and 700 university staff, including professors. So let me move to our engineering faculty. So we have and graduate course and course like this. So I'm going to show today's content here. Firstly, I introduce microcapsule and polymer particles and study on this field and shown today. So microcapsule is a spherical particle constructed by some various materials. So polymer materials such as biodegradable, synthetic, and inorganic, and like this. So typical structure is shown here. Monocore, single core structure, and multiple core dispersed droplet and matrix type shown here. Various materials we call the core materials wrapped by these materials to make particles form. The shape is spherical and oval and crushed type, and size is the submicron order. Area is quite wide, and pharmaceutical, agrochemicals, again, solvent, and so on. So we worked on the mainly extractant and solvent. So preparation is method, polymer particle is shown here. Method is divided in mainly 3 parts: chemical method, chemical method, and physical method. So typical preparation procedure using us. So shown here, firstly we make W emulsion. W emulsion is prepared by mixing solution, immiscible solution, aqueous phase and organic phase like this. So after preparation of W emulsion, so W emulsion was redispersed in aqueous solution, W emulsion. Photograph of W emulsion and W emulsion. So you can see the small upload this figure, this photograph. So small water particle in the organic solvent. And then next one is the W emulsion. So droplet is a oil droplet containing phase droplet. So after preparation W emulsion, so use some method to solidify the organic phase by polymerization or solvent evaporation. So organic phase change to liquid to solid phase, solid phase. So we can get the light particles like this containing water droplet. Spherical droplet is the trace of the aqueous phase droplet. Okay, so let me move to the preparation mechanism. So initial polymerization mechanism is three organic phase containing monomer materials polymer compound. So reaction is started by the radical polymerization. So monomer polymerize dimer and polymer. So formed polymer was deposited at the interface between organic phase and aqueous phase like this to make a wall of the particle. The second one is a solvent evaporation method.
I'm sorry, Sensei, to interrupt. I'm sorry to interrupt, Sensei. The voice is not clear. Maybe all of the audience have same problem with the voice. Yes.
Really? Can you hear me?
Yes. Yes.
No?
No, it's like maybe some freezing voice.
Yeah, really. So how? So I more loudly voice is better.
Maybe another option is
No.
to leave the meeting and rejoin the meeting, Sensei. Leave the meeting first and then rejoin again,
Yeah,
and we can continue.
Yeah, okay.
But because we have many times.
So can I continue? Okay. So I interrupted my presentation. So and second chance.
Maybe the computer need to be restart or refresh.
Yeah. Okay.
Also, same problem with
Okay.
Professor
So I
Akrajas.
try and
Yes. Yes.
okay.
I'm so,
Okay.
we're sorry. We'll waiting. We'll be waiting.
Okay. Yeah. Okay. So please start next presenter. I'm try to refresh my PC.
Refresh my PC.
Iya. Dilanjut ke presentasi selanjutnya atau enggak usah? No, we will waiting for you, Sensei. Please restart your computer and we'll waiting for you again.
Yeah, okay. Please.
Welcome, Professor Akrajas Ali Umar.
Yeah, thank you very much. Sorry, because I also problem with my my Zoom, so just successful now. Did you hear me?
Yeah, we can hear it clear.
Okay, thank you.
Shiomori Sensei. Jadi saya ini orang presentasi. Usually some people also experience the same thing related to Zoom connection. In my experience, I usually restart my computer first and then rejoin the meeting. And also, I think Professor Akrajas Ali Umar also have experienced the same thing and also perform the same solution. Yes. Shiomori Sensei. Would you try to speak and test the connection again? We are sorry for this.
Okay, so now voice is clear. Yeah, maybe the problem is the internet connection or something like that, because we can see the video is freezing, maybe, or the computer is freezing. Shiomori Sensei, is it possible to restart your computer first? Bisa videonya saya.
Okay. Okay, Shiomori Sensei. Is it okay if we move to the next presentation first, and while waiting to solve the problem? Is it okay? Okay. We are really sorry for this. Okay, ladies and gentlemen, thank you very much for your attention. While waiting for our keynote speakers, Professor Shiomori, to solve the problems with the Zoom connection, now we are going to move to the next presentation by Professor Akrajas Ali Umar from University of Kebangsaan Malaysia. Before that, let me introduce Professor Akrajas Ali Umar first. Okay, Professor Akrajas Ali Umar received his PhD in physics from the National University of Malaysia in 2004 in organic thin film for optical sensing application. Also, he is currently Associate Professor in Institute of Microengineering and Nanoelectronics in the National University of Malaysia since 2011. His research interests mainly in the field of nanophysics and nanomaterial chemistry, with the emphasis for energy conversion application, particularly to investigate the role of atomic compositions, surface structure, and shape of nanostructures in photoactivity and photoelectrical properties. And also, he has served as a lecturer at the Department of Physics, Universitas Andalas, Indonesia, from 1997 to 2008. And also, he has performed also his GSPS postdoc fellow in Kyoto University. Currently, he is a member of American Chemical Society USA and Institute of Electronic and Electrical Engineering USA. He has published more than 250 papers in high-impact journals with H-index as high as 29. That's all, I think. Pak Elisa, would you please stop screen? Okay. Professor Akrajas Ali Umar, the next time is yours.
Okay. Thank you very much, Bapak Dr. Pasjan. And Assalamualaikum warahmatullahi wabarakatuh, and very good morning. Now I would like to share my screen.
Yes, please.
Okay, can you see my screen?
Yeah, we can see.
Okay. Wait. Okay, this morning I would like to say sorry because I'm a little bit delayed for joining this conference because of my connection with this meeting. And okay, now, Alhamdulillah, we are now joining this meeting. This morning, I would like to discuss some characteristic of photoelectrical dynamic in porous solar cell, including any factor that influence this phenomena, this process. And also, I would like to discuss our recent strategy for the improvement of the nature of photoelectrical dynamic in the perovskite solar cell. I will start my discussion by giving a brief overview about perovskite and also current state of the art of perovskite solar cell fabrication. Then I will comment about current issue that always encounter in the perovskite solar cell fabrication, such as the critical phase instability in the perovskite, as well as the deficiency in the photoelectrical dynamic in the devices, which is my focus in this morning talk. And then I will discuss our recent strategy and our some approach in order to improve the photoelectrical dynamic. Then we expect we get high performance perovskite solar cell. I will conclude my talk by giving several future activity that we can explore in future for the sake of the fabrication of high stable, high performance perovskite solar cell for real application. Perovskite solar cell, as we know, that actually it is a new generation of solar cell that utilize organic hybrid organic inorganic lead halide perovskite as the active material. This is firstly reported in 2009, where perovskite was used as a sensitizer in the day-star solar cell with efficiency is around 3.x, and the performance can be improved to 6.5 within 2 years. But because of organic perovskite halide is actually an ionic crystal, it is easily dissolved in liquid electrolyte. So in this case, stability has become the main concern. Then in 2012, there is the chance, development, improvement of the structure by replacing liquid electrolyte with whole transport material, which is spirometad. Then performance can be suppressingly can be improved to 14%. Then with the improvement of photoelectrical dynamic, photoelectrical properties of the perovskite by doping, and also the improvement of the thin film properties, interfacial properties of the device, then the performance can be exponentially increased to that reach 25.2%, which is reported by Korean Institute with collaboration with MIT. With this condition, perovskite solar cell is much higher in efficiency compared to silicon solar cell. And this considering the nature of the fabrication, which is low cost, and we expect perovskite solar cell become an alternative for green energy production. Perovskite solar cell can be in the form of normal and inverted depending on the position of component in the device. For normal, we have electron transport layer on top of ITO or FTO, which is a wide bandgap semiconducting material, and then perovskite. Then we have whole transport layer, which is a low bandgap semiconducting material, then electron. Meanwhile, for inverted, just we change the position of STL and STL. Now I would like to briefly discuss about the perovskite. Maybe it is useful for those who are new in this material and also one starting the research in this field. Actually, perovskite is referred to the calcium titanate that was discovered in 1839, which structure consists of a corner sharing of the I-OSIC octahedral in 3 dimensions. Sorry, with calcium occupy the cavity inside the cubo-octahedral unit cell, and this material adopt a BX3 stoichiometry with A is monovalent metal and B is divalent metal. X can be oxygen or halide. And in 1978, the sister of oxide-based perovskite, namely halide-based perovskite, is discovered. And see, this time, this material already widely explored due to its interesting physical and chemistry properties. And as we mentioned earlier, that their application in solar cell is reported in 2009. In principle, the monovalent cation sublattice can be replaced with any cationic molecule, depending on the size of the molecule, that if they can fit into this cavity, so we can use it. If big molecule with big size, so it may destroy the structure and induce a phase transformation of the perovskite. And actually, there are large range of material with this stoichiometry, and from this periodic table, we can see several possible combination of the material which can adopt this stoichiometry. And at least we have more than 500 combination from this periodic table, where A is A cation, B cation, X can be oxygen or halide. This can be achieved by just balancing scheme in the oxide, where metal oxidation state of metal A and B sum up to 6, or in halide it sum up to 3, so we can have this kind of combination. And even the existence of this material can be further expanded by substitution of metal cation inside the octahedron. So we may produce double, triple, and quadruple perovskite as shown in this picture. Why perovskite become the center of interest, at least for last decade, last decade, for optoelectronic application, particularly solar cell and light emitting devices. Yeah, because it has excellent optoelectronic properties and high electron mobility if we compare to conventional organic semiconductor material. And this is in silicon comparison. And also perovskite offer high diffusion length, around 10. This is comparison for single crystal silicon. And actually, depending on the grain size and also of the perovskite, we can further expand the diffusion length of the carrier inside the material. For example, if we can prepare single crystalline layer of perovskite, so we may get a much bigger diffusion length. And most important phenomena that may beneficial for solar cell application is perovskite has low exciton binding energy, around 10 millielectron-volt, which is similar with silicon. Actually, this value is only 1/3 of the thermal energy in room temperature. So it means that during the photovoltaic process, we can easily dissociate electron and hole to produce photocurrent. And another interesting feature is perovskite has strong interband transition that offer law of association coefficient. This means that perovskite can absorb a large density of photon for producing of large density of keton. Then we expect a lot of photocurrent can be produced from this the device using perovskite. And another interesting phenomena that's shown by perovskite is its properties can be simply adjusted by a simple modification in the metal or cation or anion sites. For example, in this picture, the color here is actually represent the photoluminescent properties of cesium lead bromide. It can be changed to red or blue depending when we substitute bromide anion to iodide or bromide to chloride. Then even on if we, depending on the concentration of the doping, we can even control the emission wavelength. So we may produce material with desired properties and of course desired performance. And again, this material provides many more benefits. For example, the devices using the material can be prepared using solution processing, which offer us very wide flexibility and opportunity for material properties improvement as well as device fabrication cost. Now we have seen that we can imagine that perovskite may offer us many interesting properties for our aim objective for application of this material in our life. And actually, even though this interesting phenomena, but perovskite actually archetypal for phase transformation system, where this material can easily change phase crystallinity due to the simple change in the temperature or pressure, electric field during the operational of the device, humidity and oxygen, and many other triggering factor for this phase transition. And the common phase that the perovskite can has is a cubic, a tetragonal, a cubic structure, tetragonal, can be in the form of rhombic, hexagonal, and also monoclinic. And in a high performance optoelectronic device, cubic phase is required, but this phase is only stable at high temperature because of its high positive formation enthalpy. And by changing the system, change the temperature to room temperature, it can simply change to, can easily change to tetragonal, which is not optically active. So this means that our device using this material will be not function. This is typical example how the phase transformation can be seen. For cubic phase, the color of the film is black at around 100 degrees Celsius, and it changes to yellow color, which is tetragonal, which is much stable in the enthalpy, low enthalpy. It's become yellow at the room temperature. Thus, this is not photoactive anymore. So actually, this is our task for those who are interested in the field. Our aim is to find soon a suitable approach to control the stability of the device or the material, so we can realize high performance optoelectronic device in real application. Now we look at another critical issue in the device solar cell, perovskite solar cell, which is receive less attention actually, because many researchers just concentrate on the critical phase stability issue. Namely, the efficiency of photoelectrical dynamic at the interface, or ETL, as well as STL. In a typical process, during the photovoltaic process, when perovskite absorbs photon energy, electron will be excited to the conduction band, and a couple of electron and hole in this material we can then diffuse into any position, particularly at the interface with the STM. The characteristic of the dynamic of the diffusion of the carrier is that this material strongly depend on the photoelectrical properties of the perovskite, the nature of crystallinity, as well as the defect density in the devices. So some of the excited carrier can be recombined back via band-to-band transition or radiative transition, or via defect assisted recombination. So we will lose precious hot carrier in this case, so we may decrease photocurrent in this case. Okay, now let's say now acetone now successfully achieve the interface, then it may dissociate with hole, and electron will injected to the ETM. The nature of the charge transfer here also strongly depend on the nature of the surface properties of the perovskite and surface properties of the ETM or STL, and the nature of coupling between these two materials, as well as the band alignment of these two materials. So when the charge transfer is not easily occur, so electron carrier may be accumulated at the surface of perovskite, then it will again trigger radiative band-to-band transition or defect-assisted recombination. Now let's say here, after electron is injected here, the nature of transport, the dynamic here also strongly depend on the nature of properties of this material. When the transport is special, electron easily transport to the external script for photocurrent. If the transport is not occur normally, they will accumulate at the surface. Again, this will trigger recombination at the interface, and we may lose again the precious current we expect from the photocurrent photovoltaic process. And if you look at the hole that's already separated with electron, they also diffuse to the interface. And then again, the process of charge transfer here also similar with this phenomena. Okay, now we look at more detail about the dynamic at this interface. This is typical structure of the perovskite solar cell, where we have a compact layer of TiO2 on top of ITO or FTO. Compact TiO2 can be a compact layer of colloidal particle of TiO2 or thin film of TiO2. And then on top of this compact layer, we have here, we can see is a mesoporous layer of TiO2. We can imagine here how the condition or the properties of the porous structure, which is content of large porous and also content of dead pore structure, which is detrimental to the photoelectrical dynamic in the devices. If we look at the top view of this porous structure, we can imagine here that it consists of large random pore structure and also connecting colloidal structure, which also produce large scale of interfacial grain boundary resistance, which is also influence the dynamic of photogenerated carrier in this structure. So now when electron injected to the structure, it experience the structure until successfully reach the ITO. So I describe the process with this model. This is perovskite. This is ATL of TiO2. The nature of charge transfer from perovskite to particle also is influenced by the nature of coupling here. And when electron already injected to the material, depending on the coupling between adjacent particle, some of them can successfully transport to the external circuit, but actually most of them is accumulated at this interface. This will induce charge transfer at this interface, recombination interface, and also it is induced in recombination in this material, and also electron that exists on the surface of this particle may react with any oxygen molecule at the interface of the surface that will produce a superoxide, wherein then will induce phase instability in the perovskite, and this will damage our devices. So we should have to obtain highly dynamic of transport in this material. We need to improve the coupling between ETL and perovskite, also between colloidal structure in this ETL structure. So we may expect we have better electron transport in this device. For conventional spherical colloidal anatase TiO2, the surface of the particle actually bounded by 101, which is low in surface energy. The highly stable, the stablest facet actually in the anatase TiO2. When this material bring into contact with perovskite, we can expect between TiO2 and perovskite will have a weak coupling. So what happened during the photovoltaic process, because of weak coupling, only limited electron can be successfully transferred to the TiO2. So most of them will be accumulated on the surface of perovskite that will in turn drive recombination via band-to-band recombination or defect-assisted recombination. So if we prepare TiO2 with high energy facet, for example, here 001, which is much higher in surface energy, we expect better coupling, electron coupling between perovskite and TiO2, then we may have better charge transfer process. This is typical example of 001 faceted TiO2 thin film. But while 001 facet may improve the coupling, but when we use this kind of structure as ETL, as we can imagine that also will have large interfacial grain boundary resistance, so we may again lose precious photocurrent during the transport. So we need to find the to solve the problem. For example, the idea is to develop a single crystalline electron transport layer with high energy facet, and this will facilitate and realize the formation of facile charge transport and transfer and transport in the device. Thus, we will have high performance devices. This is our recent strategy, new design of ETL, namely we call as nanograss of TiO2. Actually, nanograss grow directly on the TiO surface, which is very strong, and even we cannot remove it with scratching with knife or even ultrasonic. So it is very beneficial for just extraction to the ITO or FTO. The unique structure is the nanograss actually very small structure with 3 nanometer thick, and the facet characterized with 001 high energy facet. And if we look at the individual structure, nanograss actually contain spike structure, which is actually high energy site, where active charge separation we expect to occur in this structure. So if we look at the devices using the nanograss TiO2, we can see the description from this model. Actually, nanograss will provide us with highly ordered porous structure, no dead end pores, so we can have large area contact with perovskite, where charge separation, charge transfer can occur anywhere on the body at the interface between nanograss and perovskite. Then, because of nanograss is single crystalline, and this coupling between based on nanograss visibility is very high, very good. So we may have facile transport and extraction to the external circuit. This is typical example of performance we have recently. That is a nanograss based device. We get efficiency as high as 21.6, which is among the highest reported in using TiO2. We use a triple cation perovskite system, and also fill factor is quite high, around 80%. And also we report VOC, actually we can achieve only up to 1.18 volt, but for this optimized device we have 1.16, which is also one of the most highest VOC reported so far. We compare the performance with SNO2. Why we compare with SNO2? Because actually SNO2 is much superior in properties compared to TiO2, such as SNO2 contain less defect density, and also SNO2 has much better hole blocking capability. So it is worthwhile to compare between these two materials. Then we get efficiency for SN2 based device only 80%, which is much lower compared than the nanograss based device. So we will look at what is the nature of charge transfer at the interface by doing a transient photoluminescence spectroscopy. We try to describe the nature of charge transfer between and compare between these two systems. And this is a typical photoluminescence quenching profile. And we fit this result with the exponential decay function. And we got from this function to time constant, namely fast time constant and slow time constant. Fast decay time constant actually associated with the interfacial charge transfer dynamic. And we can see here that the interfacial charge transfer dynamic in nanograss-based device is much faster compared than SNO2-based device. And this phenomena also further supported by electrochemical impedance spectroscopy result, which is shown that which show that the interfacial charge transfer resistance in the nanograph based device is much lower compared to SNO2 based device. And we fit this result with this equivalent circuit that we can get interfacial charge transfer and also recombination resistance. As we can see at this table, actually recombination resistance in TO2 is lower than SNO2. TO2, I mean, nanographs much lower than SNO2, which means that recombination in TO2 is also high, but because of the performance is high in nanographs, so we can remark here that the charge transfer dynamic and transport dynamic in the device should be much active. So the deficiency due to the recombination of the carrier can be compensated or can be overcome. So that's high performance of device can be realized. Now, to further examine how the nature of photoelectrical dynamic in this new system, we carry out the electromobility analysis in the device by fabricating electron-only device with the structure, which is we have nanographs and PCBM. Both of this material actually electron transport material, and we record the JV curve under that, and then we fit the result using Mott-Gurney equation. Then we got here space charge limited current electromobility in nanographs very much low compared than SNO2 based devices, even most of us TO2 based devices. So this is actually one of strong evidence that new design of ETL is very useful for the improvement of photoelectrical dynamic in the devices. Actually, as I mentioned earlier that TO2 actually intrinsically contain large density defect, larger intrinsic defect compared to SNO2, and it is true that in our device that using this relation between VOC of the device with the carrier density and during the photovoltaic process, we can estimate the trap density signature, and we get this trap density signature in the device of using nanographs is much higher compared to 2.8, around 2.8% higher than SNO2 based device. But higher PC in TO2 can only achieve if all of this trap or recombination can be overcome. Thus, the only reason is the high photoelectrical dynamics should be exist in these devices. This is a typical operational stability of the device, which show negligible decline in the performance up to 3%, 300 seconds during the continuous operation. And maybe we can estimate no significant decrease in the performance if we extend the evaluation. This is aging stability. We can retain 20% of the performance if we store the device for more than 2 months in nitrogen. Okay, this is we try to see how the dimension of the nanographs can influence the performance. We change the length of the nanographs from 60 to 150. Then we get optimum condition is around 80 nanometer, which is the result we already present. And actually, I would like to highlight here the VOC of the device. As I mentioned before, from the nanographs based device, we get VOC up to 1.18 volt, which is the highest reported VOC actually reported so far. And this is one indication of the facial photoelectrical dynamic in the device, which is also supported by field factor, which is high, more than 81% mostly in the device. Thus, I can summarize this new structure that single crystalline new design of ETL, particularly single crystalline with high energy facet, may promise enhanced photoelectrical dynamic in the device. Actually, we also have developed new different ETL structure. Actually, I will try to speed up my talk because time may be almost finished. Actually, 2D atom thick, two-dimensional transmission metal discalcinate, particularly tungsten disulfide. Actually, this material offer many promising phenomena, such as this material actually a high electron carrier mobility, and also because of it is ultra thin and also single crystalline, so we may get very ultra fast electron transport. And another interesting phenomena in this material, actually it has the nature of surface collective motion of exciton, which may drive it may produce a directional electric field in this material that may help to extract massive photo-generated electron from the perovskite. So we may have enhanced performance if we are using this material in the devices. And this is a typical result that we recently reported that we use a thin layer of tungsten disulfide as electron transport layer. This perovskite, this is ITO, and this is typical result of the 2D material on the ITO. This is SRT image showing us single crystalline properties, and SED also show us a single crystalline nature of the 2D material. And this is performance. We can get for this condition, we get efficiency up to 16% because of this structure is very thin. To avoid the contribution of ITO, we compare the performance with ITO, and we got the performance with device with W tungsten disulfide is much higher. So we can say that this material can function very well as ETL. And also POC is quite high, more than 1 volt, much higher compared than only on ITO. And we evaluate how thickness of TO2, thickness means that number of layer of tungsten disulfide. We vary the thickness from around 5 layer monolayer, this one, to around more than 20 monolayers. So we got the optimum condition is at the around 5 to 6 monolayer with efficiency can reach 18%. And also POC also quite high, around 1.1, and fill factor is also much higher, more than 70%. This is typical operational stability, energy stability. And finally, I would like to summarize future direction that we can make activity on this. Again, I would like to highlight here that perovskite phase stability is very critical issue here, so we can find a suitable method to make highly stable phase perovskite via proper approach such as precipitation, doping, and etc. And also, we may produce a perovskite system with high crystalline size or even single crystalline layer, so we can may further uplift the performance due to the facile transport dynamic in the devices. And finally, we may still we may continue to design new ETL structure, particularly with single crystalline as well as high energy facet to provide enhanced electronic coupling at the interface, so that we can further uplift the performance. Finally, I would like to thank the Ministry of Higher Education Malaysia and University of Malaysia for supporting this project, and also I would like to thank Bell and Rock Fellowship for visiting fellowship to Fudan University for collaboration with high performance perovskite solar cell fabrication. And then I would like to thank my collaborator from University Halu Oleo Kendari Professor Muhammad Nurdin, to whom I recently actively developed new structure of TiO2, and also Professor Isjanzan, where we collaborate for the propagation of high performance flexible perovskite solar cell. And finally, I would like to thank you very much for your kind attention. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you very much, Professor Akrajas Ali Umar, for such a great presentation with a high complexity work, I think. If you may let me to give some comments about the presentation. It's about perovskite solar cells, a new generation of solar cells. And it has some critical problems related to stability, and also Professor Akrajas Ali Umar offering great proposed strategy to overcome this trouble, like creating nanoglass TiO2, and also design a new single crystalline, and also proposing an atom stick to the ETL research program. Okay, I believe all the attendee has problems, but we need to hold it first until discussion sessions. So thank you very much, Professor Akrajas Ali Umar, for your presentation. Now we are moving to second presentation to Professor Koichiro Shiomori. Are you listening to me, Sensei? Shiomori Sensei, are you there?
Yeah.
Okay.
Okay.
Would you? I'm sorry, Professor Akrajas Ali Umar. Would you please stop your screen sharing?
Okay.
Yeah. I change PC, but
Okay.
last one is better.
Sensei, please wait while Professor Akrajas Ali Umar stops screen sharing.
Okay.
Okay. Professor Shiomori Sensei, would you start your screen sharing and test the voice first?
Okay. So now my voice is clearly.
Yeah, we can hear clear.
Okay. So
now it's perfect.
yeah.
Yeah.
Okay.
If during presentation we find same problem, maybe. Okay.
Okay. So now I change the PC, another one.
Yeah. Now it's
So
very loud and
now,
clear, Sensei.
yeah. Okay. So I'm going to start. Okay.
Okay. Thank you very much, Shiomori Sensei. Ladies and gentlemen, the second presentation is Shiomori Sensei from University of Miyazaki. The title is about recent developments of microcapsules and polymers particles for separation medium. Shiomori Sensei, the time is yours. Thank you.
Yeah, thank you very much. So I'm sorry, so my PC have a trouble. So I start my presentation today. Recent development of microcapsule and polymer particles for separation medium. So I would like to introduce Miyazaki Prefecture again. So we are in Kyushu Island, south part of Japan, southern part of Japan. So in Miyazaki Prefecture is located on the east coast of Kyushu Island here. So our university Miyazaki, have 5 faculties: agriculture, education, regional innovation, engineering, medical school, like this. So number of students is 5,000, not so large. So local university. So faculty of engineering, now we have a 7 faculty, but I working at applied chemistry. So today I'm going to present these contents. So I introduce microcapsule and polymer particles firstly. So microcapsule is a round shape polymer particle containing various core material, liquid or solid, and sometimes gas is contained in the center of the microcapsule. Capsule type is shown divided in 3 types. So monocore, single core structure, and dispersed and multiple core structure, and matrix type structure like this. So size of the microcapsule is sub-micron order to millimeter order. So application area is quite large for pharmaceutical, agrochemicals, hygiene, extractant, and solvent. So now we worked on the extractant and solvent application. So I'm going to show the preparation method of microcapsule and polymer particles. And preparation method is divided into mainly three methods: chemical, physical-chemical, and physical method. There are different preparation methods like this. We use mainly in situ polymerization in the emulsion system and solvent evaporation method from the dispersed emulsion system. So I show the typical preparation method, preparation flow of microcapsule. Firstly, we make a WW emulsion, aqueous phase and organic phase. Aqueous phase was dispersed in organic phase like this photograph shown here. Small dot is an aqueous phase droplet. After preparation of W emulsion, so W emulsion was dispersed in the aqueous phase to make a WW emulsion. Photograph of WW emulsion shown here. So you can see the dark large droplet, and large one is the oil droplet containing small aqueous phase droplet. After preparation of WW emulsion, so organic phase was solidified by various chemical reactions such as polymerization and solvent evaporation or cross-linking reaction. So after solidification, we can collect microcapsule like this. Same image is shown here. Surface is this one is a very smooth surface, and the inner side, there is a many spherical pore like this. So this pore is a trace of the inner aqueous phase droplet before the same image observation. So we dry in vacuum of the we do the preparation pre-treatment by evaporation of many organic solvent and aqueous solution. Aqueous water is removed from the particles. So mechanisms, formation mechanism is shown here. Initially, in situ polymerization method is shown here. Initially, a monomer was dissolved in organic solvent, and to make after making OW emulsion, so mixed solution temperature was raised. Radical polymerization was started, and monomer was changed dimer, trimer, and polymers, and polymer was deposited at the interface between organic phase and aqueous phase like this to make a wall of particle. next one is a solvent evaporation method. Polymer was dissolved in organic solvent after making OW emulsion. So pressure was reduced and temperature was raised. So solvent was evaporated from oil droplet. So polymer was deposited at the interface of the droplet to make a particle wall like this. So when we prepare the microcapsule and the polymer particles, initially we prepare the emulsion, various type of emulsion, OW, WO, WW here. So after preparation condition is quite affected to the last prepared microcapsule or polymer particles. So we should control diameter or stability, and the structure of the emulsion is control of the emulsion is quite important to control the microcapsule and polymer particle morphology. So various separation and purification method is used in the chemical processes. So precipitation, membrane separation, solvent extraction, adsorption is a quite typical separation method from the mixed target material from the mixed solution or gas. So we select these methods by depending on the purpose of the separation. So in the metal separation or some organic compound separation, solvent extraction and adsorption process, adsorption method is a quite popular method. So, but solvent extraction is a very important process in the metal separation in the liquid phase. So many researchers develop extractant. Extractant is a extractant is an organic molecule to interact with metal ion to make a complex, and selectivity is very important. Selectivity of the extractant is very important in the extraction system. So many researchers develop a special molecule they have a specific selectivity. So, but in the extraction process, there are many large amount of organic solvent is used in the process. So organic solvent is not good for our health. So reduce of the organic solvent is one of the problem is extraction system. So around 1990, so some researcher propose to make a microcapsule containing extractant. So Watara is Hatakeyama is first researcher in Japan. So they propose this system. So various microcapsule or polymer particle was proposed in the like this. So to use extraction system in the particle system. So now many researchers are working on this area, so I would like to introduce recent topics shown here. So selective and mutual separation of metal ion is a very important object purpose in this field. So, but basically, selectivity is comes from original extractant properties. Originally come from extractant properties and selectivity. So when we extractant was interrupted in the polymer particles, so basically selectivities depend on the original extractant properties. But some researchers reported some result. Professor Lee reported selectivity of the core shell layer on the separation of rhenium and molybdenum. So like this, MO was removed at the shell layer like this, and only rhenium can pass through the shell layer into the core of extractant. And selective separation achieved successfully like this. So next one is one example of the coating by PVA like this. So PVA coating was done on the surface of the particle. Quite thin PVA layer was formed on the particles. So extractant is contains small pore like this. So, and PVA film can only pass through the rhenium ion. On separation, selective separation was done using this type of particles. So other research relating on the separation of carbon dioxide gas, and application of removal of pollutant were done by various researchers, many researchers like this. These topics was summarized in the full paper. If it published, you can see these recent topics. So let me move to our study on this polymeric particles as a separation medium. So we reported many results on the separation of metal ion and organic compound like this. So we selected different structure shown here, 4 type, but now we focus on the 2 structure because it gives a high surface area between extractant and aqueous phase. So I will show the preparation method shown here. So initially we make a double emulsion. So inner phase is a sodium chloride aqueous solution. Organic phase is a monomer solution like this. So after preparation of W emulsion, W emulsion was dispersed in the outer aqueous phase like this. So after making a WW emulsion, So temperature was raised and to start the radical polymerization. So after polymerization reaction, we can get the WW type porous particle containing extractant. So if we want to change the extractant, so we selected another extractant and dissolve in the organic phase, and or so remove and or so we change the extractant by removing by washing by the organic solvent and impregnating of another extractant. So when we change the ratio of the organic phase and the aqueous phase, we can change the porosity and we can change the porosity of the particle like this. So when we add the large amount of inner aqueous phase, we can make a quite highly porous particle like this. And also concentration of the sodium chloride in the aqueous phase was changed. So also pore diameter can change depending on the concentration of sodium chloride like this. When we select a high concentration in the inner aqueous phase, so we can make a quite highly porous particle like this. So this slide shows a pore distribution, pore diameter distribution when we change the concentration of sodium chloride in the inner aqueous phase like this. So when we change the concentration and we use high concentration sodium chloride, inner pore diameter was moved to more large area here. So we can control the pore diameter by changing the concentration in sodium chloride in the inner aqueous phase. So impregnation of extractant into polymeric particles was done by this method. So initially, particle was washed with ethanol, and after filtration and drying, so this in this step, so firstly encapsulated extractant was removed by dissolving in the ethanol. So after removing of first extractant in this step, so next we can impregnate the another solution of extractant was added to the particle like this. And after immersing the particles in the extractant solution, so after immersing, so organic solvent was evaporated by using rotary evaporator. So polymeric particle containing another extractant we can get here like this. So this procedure is a preparation of PVA alginate cross-linking gel containing extractant droplet to make a multi-core type microcapsule. So after preparation of W emulsion, W phase is an extractant solution. So W phase is containing a PVA and sodium alginate. After making a W emulsion, so this emulsion was dropped in dropped into the calcium chloride solution to make a gel and microcapsule. So after gelation, capsule was removed to make a cross-linking by GA. So typical structure or typical SEM image is shown here. Interconnected spherical pore structure shown by PDVB is shown here. So matrix type XAD. XAD is a commercially available porous resin. So extractant was impregnated by immersion of the extractant solution, organic solution. So last one is a cross-linking gel containing extractant droplet here. So shown by PVA, ALG, GA. So you can see the in this interconnected particle structure, a spherical pore structure, you can see the large pore, spherical pore in the inner side. So this pore was made from is a trace of the inner aqueous phase droplet. So in the gel, cross-linking gel, multiple core type, so you can see the small droplet here. So this droplet was, this spherical pore is a trace of the extractant droplet. So we try to extract copper ion from the aqueous solution. So time course is shown here. So extraction amount increased by time, with time, conducting time, like this. So interconnected polar spherical pore type is a quite extraction amount is quickly increased like this, but matrix type XAD4 is increasing so slowly and reached constant value. And last one is a PVA cross-linking gel, also slow, but comparing with matrix type, extraction rate is not so slow, increasing like this. So reached around 2 hours, reached at constant value at 2 hours. So matrix type slow extraction rate with matrix type. This slow extraction phenomena is a quite popular phenomena because matrix type, in the matrix type, extractant was placed in the quite small pore. Small pore of the particle was filled by extractant solution. So small pore inhibit diffusion of the extractant and extraction complex in the organic phase. So this hindrance of the diffusion is caused by this slow extraction rate. On the other hand, so interconnected spherical pore type capsule pore particle can give high surface area between the surfactant phase, extractant phase and aqueous phase. So it gives a high extraction rate like this, but surface is saturated by the extraction complex. Extraction little bit go down the extraction rate. So like this, so reaches a constant value. but almost this interconnected spherical type shows a high extraction rate like this. So this extraction rate is basically followed by the shared second order kinetic model. So Nobu-san, so she was our student. Now she is working on the Tadolaku University. So she analyzed this kinetic result. So she found the extraction rate followed by shared second order kinetic model like this. So basically this extraction rate followed by second order kinetic model wave like this. So, but I think this second order kinetic model is quite rough analysis. So now we try more detailed analysis by the two extraction steps. One is a chemical reaction at the interface, and the second one is a diffusion of the pore, diffusion of the extractant or extraction complex in the pore of the particle. So we analyze two different stages of the extraction step. So last one, I would like to show the recent result of chiral separation of amino acid using polymeric particle impregnated with phospholipids. So same image is shown here. So DPPC phospholipid was impregnated in the surface and the pore of the particle. So this photograph shows the X-ray emission by EDX from the phosphorus element. DPPC is covered with the surface and pore like this. So DPPC, usually DPPC form a liposome. Liposome is a quite unique basic two-layer molecular particle. So this liposome has showed the chiral selectivity of the L-type amino acid, but supporting on the particle of DPPC supported on the particle also show the chiral selectivity like this. DPPC on the polymer particle show the L-type selectivity like this. D-type amino acid did not adsorb on the particle here. So time course is shown here. Only L-type amino acid tryptophan was adsorbed on the particle like this. After first adsorption of amino acid on the particle containing DPPC, so second adsorption a little bit faster than the first adsorption like this. But on the other hand, D-type tryptophan did not adsorb on the particle for after long time contact. So in this presentation, I show this topics contents. I would like to close my presentation today. So thank you very much for kind attention.
Okay, thank you very much, Shiomari Sensei, for the great presentation.
Yeah, thank you very much.
Yes, thank you very much, Sensei. If I may summarize, the presentation is mainly talking about the microcapsules. including its preparations and also a recent topic related to polymeric particles and also polymerase particle separation medium. The last is about chiral separation of amino acids using microcapsule. I believe we have some questions, but we still need to move to the next presentation, the last presentation, and we'll do the discussion session later. Thank you very much again, Shomori Sensei. And then we move to the last keynote speakers, Dr. Idris Mandang, the Dean of Faculty of Mathematics and Natural Science, Mullah Warman University. Before that, let me introduce about Idris Mandang. He was born in Pindrang in 1971. Institution is a Hydro Atmosphere Environment Research Group from Faculty of Science, Mullah Warman University. And also his professional societies. He's a member of Indonesian Association of Geophysicists, also member of Indonesian Association of Oceanologists, and also member in Coastal and Estuarian Research Federation. He finished his school in Hasanuddin University, Department of Physics, in Bandung, Institute of Technology Bandung, and also alumni of QDai or Kyushu Daigaku, Kyushu University in 2008. He also has received several awards, including Academic Recharge General Dicti from Dicti in 2011. Now, Dr. Idris Mandang is Dean in the Faculty of Mathematics and Science, Mullah Warman University. Okay, to save more time, to Dr. Idris Mandang, the next time is yours. Thank you very much.
Okay, thank you very much for time to me. Honorable Professor speak today. This I said my presentation. Okay. Okay, and then before I presented my self, I introduce my institution, Warman University, and the faculties, and the lecture, and the 1015, and the student permanent graduate, and the postgraduate. The location is Borneo Island, is here. In the roadmap for development, Mullah Warman University, a center of excellence for tropical studies. They divided aquatic in the terrestrial, in the sea trop, the center of tropical study. This is especially in the aquatic. This is the terrestrial. Okay, and today I present in my sets. This is the preliminary study, the numerical model assessment of tidal current energy resources in the waters, southern part of the Borneo Island. Of the present, the use of oil, coal, and natural gas power plant is very inefficient because it will run out due to the supplies. This of course makes use look for alternative that can solve this problem. One alternative is tidal energy power plants. Apart from this supply of this technology is also friendly to the environment and can be obtained free of charge. Okay, introduction. This is the Indonesia archipelago. The ocean cover 70% of the Indonesia archipelago, and it represents enormous amount of energy in the form of wave, wind, tidal, or ocean current, the thermal resources. Indonesia shall be able to apply this alternative technology. especially with the 5,150 stretch of east to west, and the north to south a stretch of 1,950 kilometers. Indonesia positioned as the country with the longest coastline in the world. Okay, this is the tidal energy. The tide is regular and the predictable change in the surface level of an ocean or estuary with time. Tide is driven by the gravitational and rotational forces between the Earth, Moon, and Sun, which cause the flow of the Earth surface to move in different direction. The tidal energy is compression techniques exploit the natural rise and fall at the level of the oceans caused principally by the interaction of the gravitational field in the planetary system of the Earth, the Sun, the Moon. Okay, the main periods of these tides are diurnal at about 24 hours and semi-diurnal at about 12 hours, 25 minutes. This here. During the year, this motion is being influenced by the position of 3 planets with respect to each other. This is diurnal and semi-diurnal tides per day. Now you can see in deep offshore waters, this current generally relatively small. However, in the nearshore location, currents are often increased and may be accelerated considerably around inlands or trough constructions as channel and between island. And the spring tide occur when the tide generation force the sun, the moon, and the moon extend the sun direction. In the situation, the lunar tide is superimposed to the solar tide. The sun coastline, particularly estuary, can see the effect creating tidal range to up to 70 meters. And the neap tide occur when the tide generation forces of the sun and the moon extend right angle to each other. Okay, this is the tidal energy, and this is two systems to extract energy from tide. In the first single action power cycle. This is ocean tide level, and it is power generated by the water discharge here turbine to ocean. Tidal current or tidal streams are the movement of water driven by change in the tidal height. In the deep offshore waters, this current are generally relatively small. However, in a near shore location, the current are often increased and may be accelerated considerably around inlands or constriction the channel between islands. In the first single action power cycle, and this is the double action power cycle. You can see this picture from sea to estuary, the tidal current from ocean towards estuary, the turbine and generator. This is the tide going out, and from estuary towards in the sea. Okay. The approach is commonly used for the exploitation of tidal power. This, for example, and they construct rivers or lagoons. And they usually using dams to pound the upstream water and create water heat. This is, so you can see. the future dam. So potentially it's all tidal energy. Next, this is the example. To install underwater turbines at the location where high tidal current velocity is assigned. Okay, my study is the preliminary study is to calculate the tidal energy potential in the Mahakam estuary, in Balikpapan Bay, in this Berau Delta. This is Mahakam estuary in the Balikpapan Bay in the near this Makassar Strait. The Berau Delta is located in the Sulawesi Sea. Okay, I use a numerical model. Okay, I use hydrodynamic model and the ROMS. ROMS is Regional Ocean Modeling System. This is the ROMS. Is a three-dimensional numerical model that can solve the definite difference approach to the Reynolds average Navier-Stokes equation, and using hydrostatic equation and the bussiness with explicit time step separator algorithm. And this is the ROMS use the Arakawa curvilinear horizontal grid and the sigma vertical coordinate. And the ROMS model is flexible structure that allows many options for determining the model component, including option for affection scheme, turbulence model, turbulence submodel, and boundary condition variation. And they use I use the equation, the first continuity equation, and the momentum equation. This is x direction and the y direction. Okay, I use estimating of tidal stream energy. The maximum fluid power, the Pmax. This is here the equation. The Pmax, the flow of kinetic energy a square meter of turbine should due to tidal stream. The M is mass, the U is flow of speed, and the rho is density of seawater. And the second is potential power output square meter of turbine. This is the equation. Cp is varies with the current velocity for a given type of turbine. Okay, and this is the first application in the Mahakam estuary. Mahakam estuary in the eastern part of Borneo Island. This is the delta. Okay, this is I use a boundary condition, the open boundary and the upstream boundary in the model. Upstream I use the recorded chart, and the open boundary I use the tidal constituent M2, S2, K1, and A1. And this is validation the tidal level. And the blue is the model, and the red is observation. This is a tidal elevation. This location, north part, the middle, and the from is the Makassar Strait. This is the offshore area towards in the Mahakam Delta, in the Mahakam estuary. This is the tidal current amplitude. This is the simulation results. And the output in the model, M4 is tidal amplitude is the maximum is in the area. It's Mahakam River in Samarinda. M2, S2, and K1 or O1. Okay, this is the partial variation of sea level and the average tidal current and the kinetic energy. And you can see a peak This is mean sea level on tide. This is the kinetic energy. This is the open boundary. This here open boundary towards the current from offshore area in the Makassar Strait towards in the delta area. The maximum is kinetic energy is here. Channel. Okay. This is the tide driven circulation and from Makassar Strait and towards in the Makam estuary. This is in the conditional maximum flood in the spring tide. And this is the maximum ebb tides. The maximum ebb is spring tide in the current velocity and the tidal current from Mahakam estuary or Mahakam river towards the Makassar Strait. Okay, and the second is application the model in the Balikpapan Bay. Balikpapan Bay is location in the Borneo Island, the eastern part. I use the ROMs, the model. The same is applied is the Mahakam estuary. Two-way decouple. I use the SWAN model. This is the wave generate from the wind data. This is the dynamic. Okay, and then this is tidal current simulation in the Balikpapan area. You can see this is the potential tidal energy in the Balikpapan channel. The from is Makassar Strait towards the Balikpapan area. The second tidal current simulation, the Bontang area. Bontang area is still past Borneo Island. It's 100 kilometers from Samarinda. This is the tidal current, surface temperature. This is the current factor, potential, and tidal energy is here. Okay, the application in the Makassar Strait, and you can see the current velocity in the Makassar Strait. Makassar Strait here, the near is Palu, is Kalimantan, Borneo Island. You can see current from north to south. Okay. Application in the Brau Delta. Brau Delta is location is here. You can see the map. So the sea is here. And here is the Rawan Island. Okay, the tidal current in the Brau Delta. You can see its potential energy, kinetic energy. Is here the canal. The factor is 0.25 second. The tidal current here. You can get the from Sulawesi Sea towards in the Brau Delta. Okay, this is Sam. Okay, this is the temperature in the from the Sulawesi Sea towards the Brau Delta. Okay, and the apply is the model forms three-dimensional model. This is preliminary study to estimate potential the tidal current for is energy. Okay. Okay, thank you so much for attention.
Okay, thank you very much, Bapak Dr. Idris Mandang, for the presentation. The presentation mainly talking about the tidal energy which is one of the ocean renewable energy source. And it mostly talking about the ways of extracting the energy from the tides, including using a hydrodynamic model. And also we can see the simulation. I mean, we saw the simulation about application in the Balikpapan Bay. Okay, thank you very much again, Bapak Dr. Idris Mandang, for the great presentation. Now we are moving to the discussion sessions. So far, we have several questions from the attendee. And let me read it for you. The first question is from Firman Shah to Bapak Professor Professor Akrajas Ali Umar. And the question is, how do you improve the stability of perovskite materials to exposure of the humidity, especially on the CH3 NH3 PBI3 perovskite? Can this molecule material be synthesized in high humidity condition? Thank you. Professor Akrajas, you may answer the question directly.
Thank you very much for the question. Actually, it's the stability, stability of the process is actually a very critical issue actually. And for the case of the humidity effect, actually the stability is induced by many processes such as operational phase stability during operation, or induced by electric field, and ionic migration, and so on. But for humidity, actually available approaches such as making a proper encapsulation. But the main critical issue is not about encapsulation, but the phase stability induced by the UV, for example, ionic migration, electric field, or magnetic field, and also temperature. So I think for the case of humidity, we can make proper encapsulation. And for the second question, actually for making the perovskite in high humidity, actually the problem is under high humidity, probably above 70 or 60 to 70% relative humidity, we got a problem in PBI2 dissolution. So the most critical issue is dissolution of PBI2. If the solution of PBI2 cannot be prepared properly, so maybe we cannot get a good quality of MAI, methyl ammonium lead iodide perovskite. So I think we have to control the humidity during the preparation. Thank you.
Okay, I hope Bapak Firmansyah can get the answer. But if Bapak Firmansyah still have a question, you can write down again in question and answer icons. And then we move to the next questions. The next questions is from Muhammad Yudhistira Aziz from Bandung Institute of Technology. The first question is to Shiomori Sensei. Yeah. The question is how to improve the adsorption capacity and the selectivity for each type of your microcapsules material models, such as matrix, multi-core, single-core. Any special treatment for this model? Have you evaluated the reusability and thermodynamically factor for your material? Thank you very much.
Yeah, thank you very much. Nice question. So selectivity now, selectivity of the microcapsule or the particles so comes from original properties of extractant. So we select extractant for the target metal ion or some other organic material, organic compound. So, but in some case, so selectivity is was changed by the pore structure. So if we select a small pore, sometimes selectivity was changed, but other researchers also report the phenomena of the change of the selectivity of the extractant impregnated in the polymer particle. So, but it is, when selectivity is occurred in the pore, small pore, but in that case, so extraction rate is quite slow, but so in that slow extraction rate is not good for the separation. So we select a more big pore structure, but the selectivity is go down, not so good. So now we try to give a selectivity by coating or gel structure. So we select another type of gel material having a different charge, opposite charge or different type of charge group. So now we try to change the selectivity. And also reusability is also checked. Please, some paper by our group describe the reusability of the particle. Please check. And also I can give the paper by email. Okay.
Okay, thank you very much, Siomori Sensei. So for Bapak Yudhistira Aziz, if you still have any questions, maybe you can email each other to Siomori Sensei. We can provide the email address for you. Okay, the next question still from Yudhistira Aziz to Professor Ali Akrajas Ali Umar. The question is, any special characteristic of surface to control kinetic study of electron mobility analysis? Are there any special characteristic of surface to control kinetic study of electron mobility analysis?
Okay, thank you very much. I'll try to, yeah, any surface characteristic that control the surface electromobility. Yeah, actually, surface is very critical for interfacial charge transfer dynamic. Actually, so what we expect from this process is we need to enhance the coupling of the surface with the what's the interface with any other material. And one of condition is actually we may prepare the surface with high energy facet, and of course in this case this will provide or helping for enhanced electronic coupling between the two systems, so we may have better charge transfer. But actually, not the process is not that simple, because this process also influenced by the nature of surface properties such as defect, vacancy, and something. So where we cannot control this this condition, so maybe we have to find another approach to minimize the surface defect due to the vacancy. But I think one of the most simple strategy is to synthesize the system with bounded with high energy facet. Then the rest is to minimize the surface defect. We can employ different strategies such as passivation with by doping or or another surface specification method.
Thank you very much, sir. We hope Bapak Yudhistira Aziz, it's okay. I can get the answer. Okay, next we move to the next question from Bapak Muiz Rifai to Bapak Dr. Idris. How much exactly the potential energy can be extracted from your research? Also, what kind of devices or turbines that you recommended to extract these potential energies? Thank you.
Thank you so much. This is the numerical model, the predicted with the model decrease significantly during both spring and the knee pipe, and the corresponding velocity reduced about 1.2 and 0.6 meter per second. And this is the for turbine is a next process in the future. This is just a numerical model, therefore estimate the tidal current, that energy potential. This canal is Mahakam Estuary, Berau Delta, or Balikpapan Bay. And the turbine in the kind the turbine is, maybe the feature is in the laboratory is the sign is the turbine, and therefore is especially is the tidal current in the Berau River, Berau Delta, Mahakam Estuary, or Balikpapan Bay. Okay, thank you so much.
Okay, thank you, Bapak Idris. But still have another question for you. It is from Bapak Alexander Yosef Elake. The question is there any model applications, ROMs, that we must perform in the large scale before nesting to the target area or directly to the target area? Apakah dalam aplikasi model ROMs dilakukan untuk skala besar dulu, baru dilakukan ke nesting ke daerah target, atau langsung ke daerah target? Thank you.
Direct. I don't use in the nest grid. They're from Mahakam, from Makassar State, the direct to Mahakam Estuary. The same is Berau Delta and Balikpapan Bay. I know use is nested grid. Okay.
Okay, thank you. So it's direct application. Now we move to the next question from Nov Irmawati Indah. The question is to Professor Akrajas Ali Umar. As we know that TiO2 is single crystalline that is high chemical stability and unbroken anorganic material, but does the nanograss formation will not become a barrier in electron mobility?
Okay, thank you very much for the question. Actually, we need high crystallinity properties in this case because in conventional perovskite solar cell, we have mesoporous structure and also a compact layer of TiO2. So what we just discussed in this in my talk just before, actually for mesoporous structure, actually the structure is composed of pore and also interconnecting a particle, which is at the interface of interconnecting particle. We have we call as interfacial grain boundary resistance, which is resistance is actually main concern of for the electron transport dynamic. So we need, if single crystals mean that we don't have any boundary for the resistance of electron flow in the material. So it means that we need nanograph single crystalline not will not bear the electron mobility, but even enhance the mobility of electron because of single crystalline have limited resistance to the current flow. But if we have stacking of colloidal particle, we may have a large scale of resistance produced by the boundary. Thank you.
So it does not interact as a barrier, as you mentioned.
Not as a barrier, but even single crystalline method stability is chemical stability is high, but it is also important for electron dynamic, transport dynamic. So single crystalline is very important for limited resistance.
Okay, thank you very much for the answer. Another question is from Bapak Amirin Kusmiran to Bapak Dr. Muhammad Idris. What is the software that you use for modeling and the error percentage of your model and the method to solve the equation? Thank you.
Okay, thank you so much. And the software is public. The ROMS, Regional Ocean Model System, is a three-dimensional numerical model, and it can solve the finite difference across the Reynolds average Navier-Stokes using hydrostatic equation and Business equation. The percent error of my model is the error 12.22%. The root mean square error is the core current velocity is 0.14 meter. The pore sea level, sorry. This is the error 12%. The sea level. Okay, thank you.
Thank you very much. So it is free to use software, right?
Yes,
okay.
The ROMS.
Okay. Thank you very much, Bapak Dr. Idris, for the answer. We still have 15 minutes for discussion and sessions. So if there is any questions, please just raise your hand or write down your question in the question and answer icons below your screen. We also have in this room the panelists from yesterday, Professor Dahlang and also Mr. Warwick Belcher. So maybe if there is a question from another panelist, we also open for discussion. Thank you. Okay, while waiting for the question from the attendees and also from other panelists, maybe I would like to ask a question to Shiomori Sensei. In the presentation, you display the application of microcapsules in extracting amino acids, especially the chiral amino acid like tryptophan. So is it only for chiral amino acid? Can it also be performed to all type of amino acid like positive amino acids, negative charged amino acids, something like that?
I try to check some amino acid, but hydrophilic amino acid did not absorb on the surface. Little bit hydrophobic part or little bit high hydrophobicity is need to selective adsorption on the surface because it comes from the interaction between phospholipid and amino acid is based on the firstly hydrophobic interaction has occurred, and second chiral interaction between some active functional group based on the hydrogen bond is cause chiral selectivity. So hydrophobic property little bit important in the separation, we think. So same phenomena was observed in the liposome system. So basically, so interaction is same between liposome membrane and membrane formed on the particle. But we check the property of membrane on the particle surface. So property is membrane property is a little bit different between liposome and the particle system. So structure is not fixed, more strong membrane structure is a little bit weak on the particle system because random adsorption would be occurred on the surface, not make a quietly complete two-layer membrane on the particle surface. Now we continuing research on the now we continuing research to check the mechanism. Thank you very much.
Thank you very much. Thank you very much, Shiomori Sensei. We have another question to Shiomori Sensei from Yudhishthira Aziz.
Yeah.
What is the best model of microencapsulation material for organic pollutant removal? So for
organic compound, I think our system, so porous and interconnected pore system is a good material with fast separation, quickly separation is can done by with relatively high adsorption rate. So, but other system is good, but small particle is not good for the separation system. So because so small particle is quite difficult to use in the environment, and the collection of particle or filtration is quite difficult. So little bit large particle is needed. So when we select a large particle, so that case extraction or adsorption rate go down. So depending on the purpose of the use, so we should select the diameter and the material and solvent or extractant. So, okay. Thank you very much.
Thank you very much, Shiomori Sensei. We still have 6 minutes for a discussion session, so we are still waiting for the attendee who wish to ask the questions. Okay, we're still waiting, but I'm checking all the chat, and also I'm checking all the question and answer. Okay. There is a question for Bapak Dr. Idris from Khairul Anwar. if converted to generated power, what is the approximate MW potential energy generated from tidal energy at that location? Thank you.
Okay, thank you so much. Potential energy in the tidal energy in the location is the potential in the River, Berau Delta, and the energy, the tidal energy in the from Sulawesi Sea, the Sulawesi Sea towards in the Berau area. This is the potential energy. Berau. Okay, thank you so much.
Okay, thank you very much, Bapak Dr. Idris. So I'm still checking all the chat and also all the Q&A column, but still no question, but we still have 4 minutes. So maybe I would like to ask the question to Bapak Dr. Idris Mandang. Your research in extracting tidal energy from the ocean, is it only applicable in the near land? Is it applicable in the depth, in the deeper ocean? Or no? I'm sorry, I'm not expert in this. This is a common question.
This is the preliminary study. It's only a numerical model, and I need is observation data in this Makassar area in the Sulawesi Sea. And the port is validated my model. I inform you this is the preliminary study, the numerical model only, and I need is our many observation data in the Sulawesi Sea and the Makassar Strait, the tidal energy and the tidal elevation from Makassar, from Sulawesi Sea. Observation data and therefore is validation my model.
I see.
Numerical model.
Thank you.
Okay,
Thank you very much. Okay, another question from you, Bapak Dr. Idris, from Yudhis Arasis. I think Yudhis Arasis is very, very active in this discussion session, and we are happy for this. So, Bapak Idris, have you made a collaboration with other local researchers to make the mapping your research in Indonesia? For example, in Java or in Papua or in Sumatra? So we can make the one database called cloud to trace the trace. Okay.
And the next the collaboration in this year is supporting my model, the equipment, especially in the supercomputer. And next year is supercomputer is coming with Warman University. That's for my model. And the open is collaboration and the Tadulako University and the others, and Miyazaki Daigaku, no problem. Don't say. I see is potential and tidal energy potential in the Indonesian waters, so many areas. And then my study is Mahakam Delta, Balikpapan Bay is around area. Just a numerical model.
Okay.
The collaboration Tadulako University no open, no problem. Ayo kerjasama.
So you are open for collaboration.
Yes.
Okay, to Professor Akridas Alumar, there is a response from Firmansyah related to your answer. If the CH3 and H3 PBI3 materials was degraded, are there any ways to convert back to the perovskite materials?
Okay,
So
thank you very much. Thank you very much. And actually, when the perovskite experience phase transformation. In this case, it means that from cubic phase to tetragonal at room temperature. Actually, this material is very unique. The phase can be reversed back to the original phase by simply heating the sample to around 100 degrees Celsius, so we can expect to reverse the tetragonal phase to the cubic phase again. So I think it is one of the unique properties of the perovskite. It is the phase transformation in this material can be reversible. So I think just give heating to 100 again for a minute or a few minutes, so we can get back the phase to cubic again.
Oh, so these are really good. So we can reform back the degraded molecules. Okay.
Yes, yes, actually.
Okay, okay. Thank you very much. Now the discussion session is getting interesting. So another question from Sarul Ulum to Professor Akrajas. What about the thermal stability of PSC?
Yeah, thank you very much. Actually, thermal stability also another issue actually, because perovskite have a very weak PB bond, so it can broken at around 130 degrees Celsius. So this will trigger phase instability and transfer the cubic phase to trigonal PbO2. So we have to be careful with this feature, because sometimes we need to do some doping to increase the thermal stability, but 130 degrees Celsius maybe not the operating temperature, such as under sun illumination. The temperature is not that high, so only we have to take very carefully during the selection of annealing temperature. So no need to go too high, because PB bond in the octahedron is quite big, so easily to broken.
Okay, thank you very much. I think we already, the time is already over for the discussion sessions. If the attendees still have another question, you can email directly to our keynote speakers. So our keynote speaker will be happy to answer other questions. So for our panelists, there is a request from the attendees that is it possible to get the presentation, I mean in PDF form? Is it possible to share?
Yes, yes.
Okay.
Yeah.
So to attendee, we will, after the panelists share the PDF file, will send to your email. So don't worry. So thank you very much for the panelists. Thank you very much, Professor Kuchisomori. Thank you very much, Professor Akrajas Alumar. Thank you very much, Bapak Dr. Indis Mandang. Thank you very much also, Prof. Dahlang, for attending the second day.
Yes.
Thank you very much, everyone. Thank you very much, attendee. So before we finish, we would like to take the last picture. Okay, we would like to take the last picture. Please be prepared. Pak Elisa, the host of this session, will take the picture for us. So Pak Elisa, please let us know when we are going to smile.
Okay. Sorry. Yep, everybody, all the panelists, please turn on your video so we can take a picture. Oh, sorry, mine is not good. Okay. Okay. I say count 1, 2, 3. I get it once again. So I'll make sure. 1, 2, 3. Thank you very much.
Okay,
Bastian.
thank you very much.
Thank you. Thank you very much, Pak Elisa, for the picture. Okay, I think it's a wrap up. Once again, thank you for everything. And we do hope we can do this again in the future time. So we
Yes,
hope
thank you
this is
very
not
much.
the last of us. This is not the last of us doing collaboration in conference. We hope we can do it again in the next time. Thank you very much.
Thank you very much.
Ya.
Okay.
Baik.
Buat yang bagi di parallel session, kita akan adakan penutupan. Silahkan nanti akan kami share di masing-masing parallel session, ya, room untuk sesi penutupan. Terima kasih. Jadi sekali lagi untuk para peserta yang di parallel session, setelah parallel session kita akan adakan sesi penutupan. Share-nya nanti, linknya nanti akan kami share di sesi paralel. Terima kasih.